In this presentation, we will be talking about very basic math that is expected from students that are about to take an undergraduate course on digital signal processing. Although all those equations are common in an undergraduate DSP course, we will start with very basic concepts, starting with complex numbers. These numbers have both a real part and an imaginary part. The geometric interpretation of complex numbers involves representing them on a two-dimensional plane known as the complex plane or Argand plane. In this plane, the horizontal axis represents the real part and the vertical axis represents the imaginary part. I guess the complexity starts by defining j as the square root of -1. If we let j equals to -j, we will form another number in the complex plane, which is the complex conjugated, as indicated at z asterisk, of the original z. In 1545, Cardano first introduced complex numbers in his work Ars Magna while solving quadratic equations. He used complex numbers as intermediate steps in his calculations. Gauss provided a rigorous foundation for them, introduced the complex plane, and demonstrated their importance in various fields of mathematics. We can see that this complex number in the imaginary plane forms a right-angled triangle with hypotenuse equals to r, the real part given by the red section and the imaginary part given by the green section. Euler's formula is a fundamental equation in complex analysis that establishes a deep relationship between trigonometric functions and the complex exponential function. This formula is incredibly useful in various fields of mathematics and engineering, particularly in the analysis of oscillatory systems. The term re to the j theta is also known as a phasor. A phasor with a very simplified version in the Cartesian plane is j, that by using the Euler's formula we can see that it's equal to e to the j 90 degrees. The following phasors also reduce to very simplified versions, as we can see here. Note that by using Euler's formula we can verify all these identities. Phasors are a way to represent sinusoidal functions using complex numbers. They simplify the analysis of sinusoidal signals, especially in electrical engineering. A phasor is a complex number that represents the amplitude and phase of a sinusoid. Before we continue, let's verify that that phasor can be actually simplified to only -1. As we saw before, if the angle of the phasor changes with time, it will start to rotate. The minus sign here indicates that that rotation will be clockwise, and the -3 pi then indicates that it's going to rotate 3 times 180 degrees. And let's see what happens. We can see that after those rotations, the phasor in fact becomes -1. Going back to complex numbers and the fact that they do form a right-angled triangle, we can see that that point specifically has an imaginary part of 3 and a real part equals to 2. The magnitude of this vector is just given by 2 squared plus 3 squared, square root of that, which is equal to square root of 13. The angle is calculated by the tangent inverse of the height of that triangle, 3, divided by the base, 2. We can work with those angles in degrees, but often in DSP we use radians. Transformation from the polar form to Cartesian is simply done by taking the cosine to obtain the real part and taking the sine on that triangle to obtain the imaginary part, as we can see there. Addition of complex numbers is usually done in the Cartesian plane, where we just need to add the two vectors, as we can see there, on the real part, and also add separately the vectors on the imaginary part to form this new vector that we see there in yellow. Oscillatory systems, such as electrical circuits or mechanical systems, often involve sinusoidal functions. This can be represented using complex numbers for simplicity, especially when dealing with phase shifts and amplitudes. When dealing with signals, we often represent them as sums of sinusoid functions. These sinusoids can be conveniently expressed using complex exponentials. By using complex numbers, we can simplify the representation and addition of oscillatory components in a signal. Fourier analysis leverages this by decomposing signals into sums of complex exponentials, making it easier to analyze and understand their frequency content. Then, in a DSP course, Fourier analysis is covered extensively. Multiplication of complex numbers can be done in the rectangular form. Note that j squared is equal to -1, and we can also perform the multiplication in polar form where the magnitudes multiply and the phases add. Note that we obtain the same result as before. Here is the division, also performed in polar form, and note how the phases subtract in this case. Let's add two complex numbers in polar form, and in this particular case, one of them is the complex conjugate of the other one. We will be using Euler's formula in order to derive an expression that we tend to use a lot in DSP. We note that the components on the real axis are the same, and they can add together and form 2r cosine of theta. The components in the imaginary axis are the same, but they go in opposite directions, therefore they add to 0. With the result that we found, we can actually add those two phasors into one by noticing that by multiplying that addition by e to the minus j40 and of course dividing by the same so we don't modify the value, we can actually use this result in combination with what we saw with the Euler formula to form an expression with a clear magnitude and a phase. This is something that we tend to do also pretty often in DSP. Remembering all these basic math concepts can definitely help students tackle DSP topics later on. Thank you for watching.